Okay, so just to summarize in a couple slides what we were looking at in the second half of last lesson, we were looking at something called the common ion effect, where if you try to dissolve a sparingly soluble solid in a solution that already contains one of the ions in that precipitate, it will make it less soluble, because according to Le Chatelier's rule, if you have an increased concentration in one of those ions, it's going to shift equilibrium the other way. So that was the concept we looked at. Sounds familiar? We're all cool with that? Cool. So that means precipitates become harder to dissolve in a solution rather than in pure water, where these ions in the precipitate are not present. And then we got introduced to how to do these calculations using a cheat code, a little simplification, because as chemists we're lazy. But we proved that this simplification is a valid assumption to make. So the assumption is, assume that all of the common ion comes from one source, not two sources, because of course the precipitate provides some, because very little will dissolve from the precipitate in the solution, but the bulk of that common ion comes from what's present in the solution itself, right? So, like if we've got salt water, like seawater, here, and we're trying to dissolve some silver chloride in it, assume the concentration of chloride is just equal to the concentration of the chloride in the salt water. And then you'll have that number to plug into your equation here, okay? So we write the Ks expression for the solubility product. Ks is a constant, which we know. We know the concentration of the chloride because it's told to us in the question, and we just solve for the concentration of silver. Because that's solubility. The question is, what is the solubility of silver chloride? And we're going to represent that with the symbol S as per usual, and we can plug that in for the concentration of silver since it's a 1-to-1 ratio. So we just rearrange the equation, and that's our solubility, 6.4 times 10 to the negative 8. Cool. So the last thing we did last class was check this assumption to make sure it was valid. So we checked how much comes from both sources, and we figured out that the amount that comes from the silver chloride just dissolving in pure water is a very small amount, 1.26 times 10 to the negative 5. And when you add it to the concentration of chloride, that number, when you round it to 2 or 3 sig figs, doesn't change at all. So that tells us, unless we want a number that's written to 4 or 5 sig figs, it doesn't affect that answer. Yeah.
Do we have to prove that on the exam, or do we just
I think you asked the same question. Yeah, you did. We don't have to prove it.
Okay.
You can always make this assumption, always at this level. Yeah. Cool. So one more example I want to show you. So it's not a huge complication compared to what we looked at last time. So let's just read through the problem. This is actually in your SciPads on page 251, according to my notes. Maybe you guys see it there. Look familiar? Cool. So we have 100 milliliters of a 0.1 mole per liter lead nitrate solution, and we've added it to a 50 ml solution of lead carbonate. So we are going to calculate the concentration of carbonate after the two solutions were mixed and equilibrium was reached. So we know we can write a Ks expression and all that stuff. So when in doubt, remember at level 2 what I'd say? When in doubt, for any calculations, you should do what? Yeah, mass to moles, right? This is the equivalent at level 3. When in doubt, just write the Ks expression. So somebody's like, oh, I'll write that. That'll give you par marks. That's cool. Yeah. But really the tricky part is finding out the concentration of lead to plug in, because we're mixing two solutions. And these two solutions have different volumes, and the total volume will affect the concentration, right? So if we're finding out the concentration of lead 2+ ions, we know that we mixed 100 mils with this concentration. So we see that we've converted milliliters to liters, multiplied it by the concentration, because C times V gives us what? N, moles, right? And we've divided by volume, because moles divided by volume is concentration. And this volume is what we want to look at. Where did that number come from? 0.150, so that's 150 mils. Where did that come from, Oscar?
Would be the 100 mils of the lead nitrate plus the 50 mils of the saturated lead carbonate solution.
All right, because we're looking at the combined solution. What is the new concentration of lead? Cool. So we know the concentration of lead is equal to the combined volumes and the number of moles we got in the combined volume solution there. We figured that out. Plus S. But we're going to make the approximation that very little comes from the precipitate. So we're assuming that there's not two sources of this common ion. There's only one source. So this is the common ion. We assume it comes entirely from one source, and that's just from the bulk lead in the solution. And then the carbonate, it's not a common ion, so it's just represented with the solubility symbol S. We rearrange our Ks expression and plug in our numbers. Remember, the Ks constant was given to us in the question, so we didn't need to figure that out. We just divided by the concentration there. So it's just one number divided by another. It's a pretty easy one-step calculation once you figure out the concentration. And look at this. It's 1.11 times 10 to the negative 14. So that's very low solubility, right, for the carbonate ions. That tells us, yeah, due to the presence of the common ion, it really has shifted equilibrium quite a lot to the left. Cool. Everything's working?
Yeah.
Okay.
That was like him there and just dropped on the floor. That's not what What?
Let's do another one. I want you to attempt this yourselves before we take it up. So this is another example, just like what we looked at, where we mix two solutions together. So you'll need to find the new concentration of an ion. I'll let you figure out what it is, but we have 40 mils of one solution, 25 mils of another. Give it a go. We'll take it out. So what's the common ion? I know you're still working on it, but can we just state that? Yeah, it's the bromide ion, yeah. So that is the ion whose concentration we need to find when we've mixed these two solutions.
Someone's kid was like, oh, I bet it would be funny to open the door right now.
I'm seeing lots of shaking of heads.
Too much going on.
Calculator's coming out. It's a good sign.
It's getting serious now.
Getting real. Good. Here, just looking at the previous questions and follow the steps. That's cool.
The question's gone.
Oh. Guess we don't need to do it.
Here. Oh. What's that?
There you go. Back.
Never mind, it's fine.
Equilibrium.
episode 4.
It is.
A new equilibrium.
A new equilibrium. A new equilibrium, yeah. Hope for a chemistry teacher. That's a cool jacket. Well,
It's Abigail's.
that's what?
It's Abigail's.
Okay.
This is really fancy.
So, to get letters, do you divide or times by 1,000?
Say that again.
To get letters, do you divide or times by 1,000?
You want to divide by 1,000. A hilarious way to think about it is if you multiplied by 1,000, 40 mils would turn into like 40,000 liters. Which doesn't sound quite right. Chemistry is like magic, but it's not literally magic.
Should be. That's what that's what we
Off the
should
bat.
be.
That's how you do baking.
Yeah, imagine if you accidentally added 40,000. That'd be really funny. I read about somebody who misread some measurement and ended up adding about like I think it was 5 onions or something.
Wait, what?
Yeah.
What's the context?
Something like that happened to me the other night.
Let me tell you, not from personal experience, it's important to know what a clove of garlic is. Is it?
Not a bowl, but a
Yeah,
clove?
yeah. There's
Okay.
there's a difference.
I
Do you
remember
remember
that.
when I asked you to put a clove of garlic into the cooking and you got the whole bowl?
That's what I'm saying.
Yeah.
I might have done that at one point,
Like
like
doing scones and you've got to put
ages
milk in?
ago.
Yeah.
I don't like that. because
All right, let's take this up.
Why am
So once again, the first step is to to calculate the concentration of the common ion. The common ion is bromide. We know the volume and concentration of bromide initially in the one solution before it was added to the other. So C times V gives us N. That's what we're doing. C times V. That's easy. We're going to divide by the total volume. That's the only other thing we've got to do. And the total volume is 65 milliliters. So here we go. We've got it plugged in here. So I just plugged it in directly in for the concentration of bromide. I've got my 0.150 moles per liter multiplied by the 40 mils of solution divided by the 65 mil total solution. You might be wondering why I didn't convert to liters. Well, it doesn't matter because they cancel out because I'm dividing something by a volume as well. And they're both in the same units. Whether they're both in milliliters or both in liters, you'll still get the same answer. And we multiply it by the silver concentration, which we're trying to find. And that's all equal to the solubility product constant. And when you rearrange that, you should get this number. Did anyone get that number?
I didn't even get that far.
I didn't get that
Yeah.
far either.
I got to step 2 and then
Solomon and
Get to step
Oscar? Yeah, okay.
Can you re-go over the third part?
Perfect.
Do you get that number for Br minus? Will you get the equation for Br minus?
Right, so C times V gives us N, the number of moles of bromide in the first solution before we mixed it with something else, right? So you
The HBr solution.
the HBr solution, right? Yeah. So the 40 mils times its concentration tells us the number of moles we've got because C times V is N.
Mhm.
Yeah. And then because this needs to be a concentration, N divided by volume is concentration. And I have to think about, I'm trying to find the bromide concentration in the solutions after I've mixed them both to make one super mega solution, right? And the total volume of that combined solution is 65 mils.
Why are you doing it in
Okay, cool.
milliliters?
Thank you.
I was just explaining that it doesn't matter whether you convert the numbers or not, because here I'm taking a number, dividing it by another number, whose units are the same. And when the units are the same, the units cancel. And whether it's 40 divided by 65 mils, or if you did 0.04 divided by 0.065, you will get the same answer, because they are in the same units. They're both volumes in the same units, and it doesn't matter if they're both in mils or both in liters, but you can't have a mixture of both. Consistently just choose one. The units cancel in this equation. That's why I don't convert it. If you were to do a normal calculation where the units wouldn't cancel for volume, you would need to make sure the volume was in liters. Nelly, did that make sense for how I got my bromide concentration? Yeah, cool.
and then
So the
that's
common
your
ion, what I did is C times B and divided by the total volume. That's the equation.
So Yeah, KS.
I can never tell if you have
So
multiple
you
questions
plug
or
in
not.
the-
I have questions.
You're
No, I
rearranged
don't.
to
I have
solve
questions. Okay.
Ships.
Cool. One more to look at before we do some practice problems. So this was from last year's exam. So we know that the presence of a common ion decreases the solubility of a sparingly soluble salt. The question from last year's exam was to calculate the concentration of hydroxide in solution after 25 mils of zinc chloride was added to 25 mils of saturated zinc hydroxide solution. So what's our common ion? It's zinc, right? We have a solution of zinc chloride being added to a solution of zinc hydroxide. Zinc's the common ion, okay? The first step is to calculate what? In one of these solutions, before we combine it, what am I looking for in that one solution yet?
Concentration of the common ion.
Right, we're trying to find the concentration of the common ion using this equation, right? So the concentration of zinc 2 plus is equal to the concentration times volume in its initial solution before we combine it with another. And we divide it by the total volume of that combined solution. So what have we got? We've got a concentration of 0.21 moles per liter, and multiplied by the volume of that initial solution, that zinc chloride solution, which has a volume of 25 mils. And I'm just going to keep it in mils just to be a rebel and show you that this works. And then I'm going to divide it by the total volume of our combined solution. So 25 mils of one added to 25 mils of the other, that's a total of 50, right? So 50 mils. Units of mils cancel out, right? It's unitless now, right? So we're going to be left with units of moles per liter anyways. That's why this works. So we need to take this number, multiply by 25, and divide by the total volume of 50. And that's all we do to find the concentration of our common ion.
0.105.
And we should get the number you see, well, not up there. Yeah, 0.105.
Sorry to interrupt. Do we have more, please?
Oh, tons. They're all in the cupboards over there.
Yeah. So
If
cupboards
you,
on
if you
it.
check all the cupboards, they should have about 12.
Yeah, I think Greg went through them before.
But it's actually I've got
Okay, so this is the concentration of zinc, cool, in that combined solution. Now the question is, though, calculate the hydroxide concentration, right? So that's why we've got our Ks expression. Now we just plug in this new concentration of zinc. We know the Ks, and we just rearrange and solve for hydroxide. Cool. Now, if you see on my slides, I found the zinc concentration differently from what I did on the board. On the board, I did 25 divided by 50. On there, I just divided it by 2 because I mixed two solutions of equal volume. When I mix two solutions of equal volume, the concentration will be halved. So I just used some common sense there. I'm thinking, what's actually going on in the problem? 25 divided by 50 is a half, so it achieves the same thing, right? So this is only valid when we're mixing two solutions of exactly equal volumes. In the previous problems, the solutions were not of equal volumes. In this problem here, we had a 40 ml solution and a 25, so I couldn't divide by 2. Cool. So we're going to do some practice problems now. 251 to 253. We're going to work through some, and we'll take some up later.